Right, in this video, we're going to talk about actually two more formulas that you can use to find the surface area of a three-dimensional surface. The last one we did was the parameterization method, where you uh, define your surface using two parameters. They can be any parameters. Um, this one we're going to start with. It's more, I said easier, but maybe more naturally uh, used on implicitly defined surfaces. Remember, implicitly defined surfaces would be things where your x, y, and z are all on one side of the equation. It's not solved for z. So a sphere, a plane, something like that. So gets a little detailed here, but here's the idea. So here I have a portion of a surface, and here is a small little increment of that surface. We're going to call that delta sigma sub k. Sigma is surface area, a small little bit of surface area. There's our surface, f of x, y, z equals c. And the idea now is if we look at the projection of that surface down, let's say this is the xy plane, right? Maybe this is x, this is y right here. So if we project that down onto the xy plane, we get a small little rectangle here, which we'll call delta A sub k. And the whole goal is we're going to try to figure out how this area relates to this area. It's probably a scaled version, this area right here compared to that one. And then we can just integrate over the region. Sometimes this is referred to as the shadow region of my function onto this plane, the xy plane. So how we go about doing that? If for our little patch here, there's the green here is my actual patch, that's delta sigma sub k. If I did a parameterization, if I did an r sub u and an r sub v, we know from the previous video that the cross product of that would be the area of the, at least the tangent plane above this little patch. And so we'll refer to that as delta p sub k. And here below again is my little area on the xy plane. And okay, we're going to define p is a unit normal vector to the plane that we're projecting our patch over. So if this was onto the xy plane, p would be a unit vector normal to the xy plane. So if that was the case, p hat would be k hat. It's going to be a unit vector. If I was projecting onto a different plane, like the xz plane, my p could be j, or my p, if on the other plane, could be I. So typically p is just going to be I, j, or k, most of the time k, because it's most of the time we're going to project onto the xy plane. Okay, so what is the relationship here? P, if I bring that up here, would be standing vertically, whereas my cross product, which is r sub u crossed with r sub v, would be pointing perpendicular to both of those, and that's going to be at some different angle besides straight up, because this is probably slanting down the way the surface is. And so, and that's also, by the way, that's the gradient of my function. Remember, that's one of the properties of the gradient of a function is it'll produce a vector that's perpendicular to the surface at that point. So we can see there's going to be a little tiny angle most of the time between the gradient, or RU crossed with RV, and P, which would be the pointing straight up. So that angle, I'm going to call it alpha. Looks like a different letter that I'm not sure the name is, but I'm going to call it alpha. And so how we get this, so we're going to estimate the area of the surface, sigma sub k above here, directly above the shadow region, delta A sub k, by using the parallelogram patch. That's this RU crossed RV from the tangent plane. And remember, that's the area of the parallelogram. Now, the part that's a little bit tough with this formula is you need an advanced math class to show that the area of the projection the scaled area of the projection from your patch of your surface onto the projection plane, the plane whose normal is P, is given by the magnitude of R cross U, R sub U crossed R sub V dotted with P. That will give you the area. So if I take that definition of the dot product, that's the magnitude of RU crossed RV dotted with the magnitude of P times the cosine of alpha, that angle between these two here. Now, this is literally the area of our patch, delta P, of our parallelogram patch. The magnitude of P is always 1. And so what that's saying then is the area on my projected plane, on my shadow region, is going to be equal to P sub K, the area of P sub K. There we go. If I divide by cosine of alpha, right, because this is 1, then the area of P sub K is the area of A sub K divided by the magnitude of the cosine of alpha. Now, so I can think of this, they're related, they're equal to each other. I just have to divide by the cosine of alpha from A sub K, and gives me P sub K. So you can think of this term as sort of the scaling factor of how much does the area change when it's on the surface versus when it's projected down onto the plane. So I want a relationship for this. I want to figure out what that is, because in general, it's pretty hard to figure out what that angle is. So over here, also by the definition of a dot product, if I were to do the magnitude of the gradient of F dotted with P, that's equal to, remember, the dot product is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. And we're doing magnitude here, right? So that's why this is an absolute value. So I get the magnitude of the gradient of F, magnitude of P, which is 1, times the magnitude of the cosine of alpha. So what that means, if you divide by cosine of alpha this side and divide by magnitude of F dotted with P, I can solve for 1 over cosine of alpha is equal to the magnitude of the gradient divided by the magnitude of the gradient dotted with P. And I can put that in right here. That's all I'm doing. 1 over cosine, 1 over cosine. I'm putting this in right here. So there we go. The area of my little patch is this fraction, the magnitude of the gradient of F divided by the magnitude of the gradient of F dotted with P times whatever the area of my little rectangle is on the plane. Again, show you the picture again. That's how I get from this area, this patch right here, to the area of the patch down below. It's just a scaled version of that. And so I could just integrate this formula over the entire region in the plane. Most of the time it'll be the XY plane. So there's a new formula for how to find the surface area. So let's practice using this. I want to find the area of the cap cut from the sphere, x squared plus y squared plus z squared equals 2 by the cone z equals the square root of x squared plus y squared. So there's the cone. Here's my sphere. The cone's going to intersect the sphere. But all I want is the surface. I want the area of this part, of the top part. Okay, so well, for one thing, since this is related to this is my function. This is my function f. So that part of the formula, the gradient of f would be literally, remember the gradient's always perpendicular to the surface. That's the gradient of f. When we say integrate over the region, the shadow region, what we're talking about is if I project this surface, the top part of that cone, the sphere part, onto the XY plane, you're going to get a circle. And that's what our region is. Now, how do I find that? notice that R is the intersection. R is the intersection of my cone and the sphere. Cone and sphere. Yeah, it's pretty hard if you try to like solve one for z and set them equal to each other, but kind of equivalently to that is if I take this one and solve it for z squared, x squared plus y squared, and I put that in, this is basically the same result. If I put that in for this z squared here, then I end up getting x squared plus y squared plus another x squared plus y squared equals 2. So that means I have 2x squared plus 2y squared equals 2. If I divide both sides by 2, I get, that's just a circle with a radius of 1. That's this region right here. Now in the formula, for surface area, we need the gradient. We know how to find that. There's that vector p, which is kind of mysterious. That's the vector that's perpendicular to the plane that we're projecting this region down to. So what would be a unit vector perpendicular to this plane? In this case, p is just going to be k hat, the unit vector. So let's start calculating things. So we need the gradient. Gradient of f is made up of your 3 partial derivatives. So we're going to have 2x, 2y, 2z. We have p being equal to k. Part of the formula we saw, I'll put it up here, it involves the gradient dotted with p. So, and we also need to find the magnitude of this gradient. Why don't we just do the magnitude of the gradient next? So the magnitude of the gradient is the square root of 2x squared plus 2y squared plus 2z squared, which is the square root of 4x squared plus 4y squared plus 4z squared, which if I take out the 4, gives me that. Now remember, we're on the surface. We're talking about the surface here. So what does x squared plus y squared plus z squared equal on the surface? It's always going to equal 2. So this just equals 2. I get the square root of 4 times 2, the square root of 8. I suppose that's 2 root 2. So the magnitude of the gradient actually worked out pretty nice. The last thing I need is the gradient dotted with p, which in our case is the gradient 2x, 2y, 2z, dotted with k, which is 0, 0, 1. Pretty easy to see that that dot product, the first 2 terms are going to be 0, and I'm just going to get 2z. So then surface area, we're going to integrate over the region, over that circle, and it's the magnitude of the gradient divided by the magnitude of the gradient dotted with p, dA. The magnitude of the gradient worked out nice. That's just 2 root 2. And okay, I didn't do the magnitude, but the magnitude of 2z, at least in this case, z is always positive, so it's just going to be 2z. Who's cancel out. Now, I don't really want to integrate with z because the region I need to describe, this circle, is just in the xy plane. So let's also go back. What would z equal? Again, everything has to do with the sphere here. It has nothing to do with the cone. That was just where we cut the sphere off, right? That's the only thing the cone had in place. So if I solve for z, z is going to be the square root of 2 minus x squared minus y squared. So I put note x squared plus y squared plus z squared equals 2 implies z is equal to the square root of 2 minus x squared plus y squared. That's what I'm going to put in for z, and since that has something to do with a circle, it's probably a good thing to switch to polar. In polar, z is equal to the square root of 2 minus r squared. So then my integral becomes root 2 over the square root of 2 minus r squared. I guess cylindrical is what we're doing. So remember, in cylindrical coordinates, it's r dr d theta. For our circle, we had a unit circle here. We know how to do that. The radius of our circle is 1. So we're going to have r vary from 0 to 1. Theta go from 0 to 2 pi. And this is hopefully a doable integral. Root 2 is a constant. You can do a u substitution. If you let u equal 2 minus r squared, your du is going to be equal to negative 2r dr, which you can make work because you have the r there. So I'll let you finish that because I think the setup is what I get most questions on here. You should get an answer of 2 pi times 2 minus the square root of 2. Let's try another one. We're going to find the area of the region cut from the plane x plus 2y plus 2z equals 5 by the cylinder whose walls are x equals y squared and x equals 2 minus y squared. Let's draw just the walls first. X equals y squared, that would be parabola going to the right. And x equals 2 minus y squared would be a parabola starting 2 units on the x-axis going backwards. So that's going to look like this. So there is a region enclosed here. And just by inspection, I can see that if y is 1, both x is going to be 1 in both cases. So this point is 1, 1. This point is negative 1, 1. Now, the actual three-dimensional solid, if you imagine this in the xy plane, so we have something kind of coming out this way, coming out this way, and then getting met with the parabola going the other way. So here's our region R going straight up, because it's a cylinder, just like a circular cylinder. And above it, we have this plane. Okay, we could graph that plane. Actually, we could find all 3 of the intercepts, but let's just presume it's a plane that's not flat. It's coming at an angle. So let's say it's coming down like this, right? What our surface is at some point, this cylinder, when I bring it up, it's going to intersect the plane. And you'll get sort of probably the same kind of shape here. I drew it looking like a circle, but I bet it's more like the shape down here. This is what we're trying to find the area of. Here's our plane. X plus 2y plus 2z is equal to 5. Now the area of the surface, just like the last one, doesn't really have to do with this. This just gave us the bounds, right, for our region. It's this. This is our function that we're dealing with. So in our formula for surface area, magnitude of the gradient of f, magnitude of the gradient of f dotted with p, dA, this is going to be our f. This is our f. So what is my gradient? Oh, well, what is p? P once again would be k, because I'm projecting this down onto the xy plane. So this would be p, k hat. That's my area that I'm going to use to integrate, put bounds on my integral. My gradient f, partial derivative with respect to x, y, and z. This is kind of nice because I just get numbers. In fact, we're going to need the magnitude of the gradient. That's just going to be the square root of 1 squared plus 2 squared plus 2 squared, which happens to be the square root of 9, which is 3. That works out nice. The gradient of f dotted with p is going to be, and we'll do the magnitude of that. So we're going to do the magnitude of 1, 2, 2 dotted with, since my p was k, that's going to be dotted with 0, 1, 1. Nope, 0, 0, 1. And that'll just give me 2. So this one worked out pretty nice. The numerator is just 3, the denominator is 2, so I just need to do the integral over this region of 3 halves, and then just put limits over this region here. This one's going to work out better if I do horizontal cross-section, so I'm going to want to do this as a dx dy integral. Right-hand bound would be the backwards parabola, so x is going to go from 2 minus y squared to y squared, and my y is going to go from -1 to 1. Again, this should be a pretty easy integral to do at this point, so if you work this out, you should get a final answer of 4. Let's set up another one. We're going to find the area of the cylinder sheet, y equals x to the 3 halves, where x goes from 0 to 4 and z is between 0 and 1. And I just reminded you, what that's not a super well-known graph, but the graph of y equals x to the 3 halves in 2D starts at the origin and just kind of curves up, similar to a parabola, but it's not a parabola, of course. So how that would look on the 3D plane, if I, let's see, so it's kind of curving up towards the positive y-axis. So if I have it going like this, and then the idea, remember how it works, since there's no z in there, you're going to extend this upward from 0 to 1. So let's say this is 1. Oh. And let's say this is 4 right here. So maybe if I do this, this would go straight up. And I'm going to try to draw the same there. There we go. So this sheet right here, it's like a curved piece of paper, right? That's what we want to find the area for. And I chose this one because, while I said a lot of times in that formula, the shadow region, your p vector that's perpendicular to the plane that you're using as your shadow region, a lot of times p you're projecting onto the xy plane. But here it makes a little more sense to project this area back onto the xz plane, because everything's going to fit inside this rectangle that has x going from 0 to 4 and z going from 0 to 1. And so in this case, your p vector is going to be j hat. It's the vector pointing out in the y direction. And now the other thing too is this, in our formula, we have the gradient of f, and I said at the beginning that this works out better when your functions are implicitly defined surfaces, because then it's all ready to go, right? You can take the gradient of something like this really easy, partial with respect to x, y, and z. That doesn't mean we can't do this. It's just I need to now think of my function f so that I can take the gradient. We've done this before. I'm going to think of my function f as x to the 3 halves minus y equals 0. So then if I talk about the gradient of f, which is my partial with respect to x, y, and z, I'm going to get 3/2 x to the 1/2 for the partial with respect to x, and -1 for the partial with respect to y, and there is no z. So that would just be 0. The magnitude of my gradient, square root of 3/2 x to the 1/2 squared plus -1 squared plus 0 squared. So this is just the square root of 9/4 x plus 1. And then I have the magnitude of my gradient dotted with p, which is just j hat in this case. So 3/2 x to the 1/2, -1, 0, dotted with 0, 1, 0. That's going to be 0, -1, 0. So I just get the absolute value or the magnitude of -1, which is just 1. So this turns out to be then, when I set this up as a double integral, the magnitude of the gradient over this, which is just 1. So it's just going to be the square root of 9/4 x plus 1 over my shadow region, which is just a rectangle. So I could set it up either way. I think I'll do dx dz. X went from 0 to 4, and z went from 0 to 1. You should be able to do this integral, just do a little u sub here, work this out, and you should get an answer. I got 8/27 times 10 to the 3/2 minus 1. And I just want to point out too, if you watched the previous video and you did the parameterization method for finding surface area, depends on how you feel. Now that you've seen a few examples of this, even though the formula looks a little bit intimidating, many times it's not that bad. And just to point out, you could still do the parameterization formula method for this one in particular, but probably both of the other ones we did. We could have used the other formula. So just a reminder that there's other ways we could have done this, right? If I wanted to do it the old way, I'd have to do a parameterization of 2 variables, and it's really not that bad. I would just let x be x, y's got to be x to the 3/2. So I have x and y in terms of just one variable, and I could just let z be z. So in other words, my parameterization for this function is going to be a function of x and z. It's going to be x to the 3/2 z. And if you remember how this works, you need r sub x. Partial derivative of this with respect to x is 1, 3/2 x to the 1/2. Partial of z with respect to x is 0. Partial derivative of this with respect to z is going to be 0, 0, 1. And if you do the cross product, what do we end up getting? We get, for the I component, just 3/2 x to the 1/2. For the j component, it's automatically minus, but we get just 1 and 0, so -1. And for the z component, 0 minus 0, so that's 0. And remember, with this method, you're just integrating over the region the magnitude of r, in this case, r sub x crossed with r sub z over the region. What is the magnitude of that vector? Well, it's the square root of this one squared, which is going to give you 9/4 x, and plus this one squared, which is going to give you 1. And you can see that is exactly the same integral once you put limits on it, as what we got when we did the gradient method. So I find it comforting to know that for many of these surface areas, I could probably use either formula. It's just oftentimes one is easier. Okay. Now, I mentioned at the beginning that I was going to share two other formulas. I showed you the gradient method. I'm going to use this example to show you there is a third formula that you can use to find the surface area. But let's first use the gradient formula to find the area of the paraboloid z equals x squared plus y squared from z equals 1 to z equals 4. That's one of our most common surfaces, paraboloid, opening up around the z-axis. There. Something like that. But we only want the area, surface area of this from z equals 1 to z equals 4. So let's say this is 4, this is 1. So you have to kind of imagine a circle going around here to here. We just want this region, this area around the paraboloid. We don't want this part below that. Okay, so our shadow region, kind of think about this, is this part's going to come down the top part and form a circle on the XY plane. And so is this. That would come down here. So the actual region of integration is just going to be this little ring here, right? That's R. So clearly, again, our P vector is going to be K. So P is equal to K. We have to do a similar thing as the last one. This one is not an implicitly defined function. So I'm going to let F, all I got to do is move everybody over to one side, x squared plus y squared minus z equal to 0. And now I can start talking about a gradient. 2x, 2y, negative 1. Magnitude of my gradient. Square that, square that, square that should give you 4x squared plus 4y squared plus 1. Magnitude of the gradient dotted with, in this case, k. 2x, 2y, negative 1, dotted with 0, 0, 1. I'm just going to get 1. Well, technically negative 1, but when I take the magnitude, I'm just going to get 1. So I end up with magnitude of the gradient over the magnitude of the gradient dotted with k gives me the integral 4x squared plus 4y squared plus 1 over 1 over my region, which I can tell has something to do with these concentric circles here. So that suggests I should switch to cylindrical coordinates. So I can think of this as 4 times quantity x squared plus y squared plus 1, which is 4r squared plus 1. If I'm going to switch to cylindrical, then I have r dr d theta. Oh, I never did find the radius. If you set 4 equal to, that's your upper bound on your circle, 4 equal for z, that's going to give you a circle with a radius of 2. So the outside circle has a radius of 2, and if you set 1 equal for z, you get an inside radius of 1. So the concentric circles have radii of 1 and 2. So your r is going to go from 1 to 2, theta is going to go from 0 to 2 pi, of course. This is another pretty easy U substitution. Let U equal the inside. It's going to work out. And you can show that this area comes out to be, so dot, 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 pi over 6 times 17 to the 3 halves minus 5 to the 3 halves. But I want to use this example to show you another formula for a very specific case, although I think we could probably generalize this formula. This was another one where my function wasn't implicitly defined. It was solved for one of the variables. And we know in the world of 3D functions, very common to have functions written as z equals, right? Paraboloids, cones, things like that. So if you have a function that is solved explicitly, in this formula, I'm just going to write for z equals a function of x and y. I'm sure we could do it for y equals a function of x and z and so forth. How did we deal with it? Well, we let f, we just moved f z over and called it f of x y minus z equals 0. My gradient is always going to have the form. I'm going to take the partial of this with respect to x, the partial with respect to y, and the partial with respect to z, which is always going to be -1. And if I dot that, my gradient f sub x, f sub y, -1, again, it's for z equals f of x, y. So we're going to be, our shadow region would make sense. It's always going to be k. I just made a random paraboloid here. So that would be with the vector 0, 0, 1. I'm always going to get, we saw in the last one, this will be 0, this will be 0. I'm going to get -1, but in magnitude, that's just going to be 1. So my integrals, this formula is always going to have this form. It's going to be the square root. The magnitude of f is the square root of f sub x squared plus f sub y squared plus -1 squared, which is 1. And I can just integrate that over the region because, again, my denominator is just going to be 1. So if you're working with a function that has the form of just z equals a function of x and y, you could just go straight to this and you don't have to think about parameterizing. You don't have to think about, your p vector. You can just go straight to that formula and it should work for you. All right. Hopefully this has been helpful. Please let me know if you have any questions in the comments or corrections. If I've made any mistakes, please let me know. Thanks.